Alright, today we're going to talk about a classic analysis definition. It's the definition of continuity. So this is, this is just a classic definition in math in general. Usually we learn that, a function is continuous on an interval if you can, write the function without lifting up your pen. So, this function is continuous, but this one, if I have to lift up my pen, it's not continuous, it has a discontinuity. But, there's also the analysis definition, right, which is a bit more professional. And it basically says that f of x is continuous at a point x0 if for every, first I'm just going to read the definition and then I can actually explain it a bit more. But basically for every epsilon greater than 0, there exists a delta greater than 0, such that for every x in the domain of f, and also the x has to be in this range, so in the range x minus delta, x plus delta, so for every x in this range, the difference f of x minus f of x0, so f of x0 is the point we're looking at, this difference has to be less than epsilon. And now this definition usually never makes sense when you think about it. So you usually have to see it graphically. So basically what we're trying to say is that for every epsilon, here I already drew this, I can delete this. So here we chose an epsilon belt. This is our point. We're looking at this point. We're looking at x0. So this is our point here, and this is f of x0. And basically we're choosing a random epsilon, so we can choose it this big. This is epsilon. So we got f of x plus epsilon, we got f of x minus epsilon. So this belt is 2 epsilon. Basically this, for this belt, we can find a delta such that in this range, x0 minus delta, x0 plus delta, any x value in this range, if we do f of x0 minus f of x, where we can choose any x here, the difference will be, we take the absolute value because we can swap these two, it doesn't matter where it is, the difference will be less than epsilon. And that's the definition basically. And so we can see that for any function, we can choose a belt. This is our point at x0. We can choose a belt here, and then we basically just draw the line where it intersects with the function, and then boom, this is our delta belt. And basically, if we choose random x, let's say choose an x here, boom, this is f of x. So we can see that f of x on the y plot will be here, and the difference f of x0 minus f of x will be this much, and we can see that this difference is less than epsilon. This difference is this big, epsilon is this big. So basically, any x in this range will satisfy that, will satisfy this. And the important thing to know about this definition is that basically it depends, the delta depends on the choice of epsilon. So for example, it depends on the choice of epsilon, and it depends on the choice of x0. So for example, if we chose our x0 over here, if this would be our x0, so this is our point bang. So here it would be f of x0, and if we use the same epsilon range, so this, if we actually draw the range here, we can see that the delta x range will be way smaller. This is x0 plus delta, this is x0 minus delta, and we can see that the range will actually be much smaller when the function is steeper. So basically, how big this delta range is depends on the choice of x0, but it also depends on the choice of epsilon. If the choice of epsilon was way smaller, if our belt, for example, was tiny, let me use pink. If our belt around x0 was way smaller, like let's say this was our belt, so the choice of, the range of x's we can pick are also way smaller. But we can kind of see how this makes sense for, basically any function satisfies this. That's kind of the, it's kind of a weird definition, but every function basically satisfies this definition. There is some examples that don't. So for example, and f is continuous on its domain if it's continuous at every x in its domain. So we checked for x0, we gotta check for every x on its domain, and then we can know that it's continuous. Basically now we can look at some examples where we can use this definition to see that the function is not continuous. So here we have a piecewise function. So basically the piecewise function says if x is less than 0, the function is 0. So it's here in blue. And if x is greater than or equal to 0, then the function equals 1. So here it's colored in because here it equals 1. Here it's not colored in because it's not defined. The function is nothing at this point, just like the classic notation used. And basically, if we choose, if we look at the point x equals 0, so is f of x continuous at x equals 0? Well, we can check. Basically, we can choose f of x0, we can see equals 1 because if x is less than greater than or equal to 0, it equals 1. So this is our f of x 0 point, and if we choose any epsilon belt around it, so f of x plus epsilon, f of x minus epsilon, any epsilon belt, like say this one. Now we have to find the delta belt where f of x 0 minus f of x will be in this belt, but we can quickly see that any delta belt we take, so this is 0, this is 0 plus delta, this is 0 minus delta. Any belt we take here, we can basically see that the function, the difference f of x 0 minus f of x delta, like if we look here, it's gonna hold, because this will be this is gonna be basically 1 minus 1. So the difference will definitely be less than epsilon, because the difference will be 0. But the belt also goes into the negatives, and any x here, f of x here will just be 0. So the difference is going to be basically 0. The difference is going to be 1. So f of x 0, which equals to 1, minus 0, and that difference will be 1. So if we choose an epsilon, for example, equals 1/2. So if you choose an epsilon which is 1/2, then we can see that this we can't find the delta belt. No matter how small the delta belt gets, there's always going to be we're always going to have a point here where the function equals 0. So 1 minus 0 is 1. So it's not continuous. And we can do the same thing for this function. This is just 1 over x. The function isn't even defined at x equals 0, so we can't even say anything about it. But we can define a piecewise function saying that at x equals 0, the function equals 0. But now we're wondering, like, is this function continuous? Well, we can check, and basically, we can choose an epsilon belt. For example, this can be our epsilon belt at x equals 0. So basically, this is 0 plus epsilon. This is 0 minus epsilon, and we can quickly see that we can choose a delta belt. For example, like this big. So this is x. This is 0. This is delta, this is minus delta, and we can see that x is here, hold, so if x equals this, then the function here, the function will be here, so the difference 0 minus that will definitely be less than epsilon. But then when we get closer and closer to to 0, the function kind of explodes to infinity. We get very close here, the function will equal something very big. So we can choose a very small epsilon. We can even choose an epsilon difference of 10. It doesn't matter, epsilon can be 10. But no matter how small this delta belt is, eventually when we get close to this range, when we get close to 0, the function explodes to infinity. So no matter how small our delta belt is, we're basically going to have that for every epsilon greater than 0, there exists a delta. Basically for any delta, the difference f of x0 minus f of x will always be, you see, in the classic definition, we have that the difference has to be less than epsilon, but here we see that the difference actually goes to infinity. So it's going to be greater than epsilon because when x gets close to 0, f of x0 just equals 0, and f of x goes to infinity. So basically this function is also not continuous. This piecewise function is not continuous using the definition. And yeah, that's basically the definition of continuity. Most functions, like x squared is continuous, like everything, sine x, all these functions are continuous. Y equals x is continuous, but some functions aren't. And that's basically it.